All right. Good afternoon, everyone. Let's start. So first of all, I'd like to say that we have one more homework. It's going to release on, I believe, should be this Friday. And then we have a few, I think, 4 or 5 lectures to the end of the semester. I want to emphasize again, we don't have a final exam, so don't panic. So what you need to do is just finish the last homework, and also they wrap up your final project. And you do need to submit your project report so that we can collect all of your assignments and submissions and finally give some grade. So if you have any questions regarding those setups, I mean, because we're going toward the end of this semester, just let us know. And if you want to pre-estimate your grade, just look at cost policy, because we have some like 60%, if my memory is not is correct. No, I guess it's 40% of, I forgot. But anyway, just the assignment take a big portion, project take a big portion. I think this is these 2 components, and you can just do the estimation based upon that. Right. Okay. So today we're going to first wrap up our Hamiltonian Monte Carlo sampling, hybrid Monte Carlo sampling, and then we'll switch to our final topic about things we're going to discuss. Right? It's called Bayesian neural networks. Okay, so I think at end of the last lecture, we have introduced all the necessary details about Hamiltonian sampling or hybrid Monte Carlo sampling. So I would emphasize that the key idea is to construct the chain that uses a dynamic system to generate sample proposals. It's not like I'm gonna come out a conditional probability to generate this proposal like symmetric Gaussian. Instead, it generates candidates through involving some system, right? And for HMC, it uses Hamiltonian system. And we have provided the general theorem actually can be used to, like, you can design any dynamic system, right? As long as you follow that theoretical framework, you can construct valid Markov chain. But why HMC is so popular? Because Hamiltonian system has a lot of good, nice properties. You don't need to worry about like determinant of Jacobian and those kind of things. Right? So let us give a quick review. So what is Hamiltonian system? So basically, you can assume there's some kind of closed system, right? And there's some kind of surface. You got a ball. You got a small ball, right? And you got when you describe the status or state of this ball in your system, actually describes by 2 things. One is the position. One is the momentum, right? And so we can use a pair of variables, momentum and position and momentum, to describe the status of the ball at any time in this system. Right? And of course, according to basic physics, we know that the energy of this system actually consists of 2 types of energies. One is the potential energy, purely determined by the position, right? And the other is kinetic energy, purely determined by the momentum, right? So remember, and just be aware, the momentum includes not only the scale, but also the direction, right? So if this ball is states, meaning position and momentum, evolves following the rules, like the time derivative of the position is equal to the partial derivative of the moment of the energy with respect to the momentum, while the time derivative of the momentum is equal to negative partial derivative of the position. If this small ball, its states evolve following this rule, I mean, satisfy these equations, their time derivatives, then we call this system as a Hamiltonian system. This is the definition of Hamiltonian system. And and by the way, Z and R is not necessary to be restricted to like three-dimensional space. It can be any high-dimensional space. It's a kind of like abstractive and general space. Right? So the most prominent property of Hamiltonian system is that following this rule to evolve this ball, you guarantee that your energy doesn't change along with time, because the total derivative of the energy with respect to time t is simply zero. It's very easy to show that. So, and then how do we leverage or construct such a Hamiltonian system to help us to generate sample proposals, right? So in our Markov-Chain Monte Carlo sampling, we're gonna, because we always represent our probabilistic model by a John distribution, right? Z and D. D is actually the observed data. So we're gonna associate the position vector in this Hamiltonian system with the actual random variable we want to generate samples from the posterior. Right? So correspondingly, we define our position, we define our potential energy as a negative logarithm of the joint probability of your probabilistic model. That's our definition. So by the way, the definition of this Hamiltonian system, how you define energy, how you define potential energy, how you define kinetic energy, is kind of like arbitrary. You can define according to your own need, as long as you must ensure the system evolves in this way. This is the valid Hamiltonian system. That's why we can define our own Hamiltonian system where the potential energy is negative log joint probability, right? And then we can define the kinetic energy, and its most common choice is just a quadratic form with some R transpose M inverse R, where M is kind of a positive definite matrix. Okay. So then, based upon the summation of the potential energy and kinetic energy, we can construct a distribution of the state. So remember, the state of the system includes both the position and kinetic, right? So actually, through this, you actually construct a state distribution which is proportional to the negative energy. This does have some physical meanings. And if you do this, you find that this is essentially the joint distribution of your original probabilistic model multiply a Gaussian random variable R with zero mean and covariance SM. So you can see that when we construct this Hamiltonian system to facilitate our Markov-Chain Monte Carlo sampling, we essentially construct an augmented joint probability, which is shoving a totally independent random variable R. And then the idea is, okay, every time when we use another color, in our Markov-Chain Monte Carlo sampling, right? Every time, like step n, suppose my current sample is Zn. Right? So to generate the next sample, Zn plus 1, I'm gonna initialize the state of the small ball in our Hamiltonian system by setting Z as the current sample Zn in our chain, and R is just random number generated from this Gaussian distribution. I give some initialization of my Hamiltonian system, and then I evolve my system following these rules. And then I pick up any time, like a particular time t, I just read out the state. So ZT and RT, and then use ZT as my sample candidate or proposal. Right? And of course, then we need to do some acceptance test. That's the whole idea. So you can see, to generate a sample proposal in a Hamiltonian sampling idea, we're going to consist of two steps. First, we're going to randomly generate a momentum random variable typically from a Gaussian distribution. Then we just evolve the system. This evolution itself is kind of like deterministic. Right? Then we pick up the state at some time, designated time, and then we just read out the state and use that as our sample proposal. And then we do the Mitropoli-Hastings test. So that's the whole idea. We won't be able to go through the details again because we have done that before. So just to give you a sense. So and basically we can show the validity of this thing from the general theorem. The theorem we have gone through in the last lecture, and we particularly mentioned that like this theorem applies for any dynamic system if you want to use that dynamic system generate sample proposal. But in general, you have to consider after you evolve the state, your dynamic system to up to some time t, you have to compute the determinant of the Jacobian of this evolution. So you start from this state, it just evolve sometime to the next state, right? This state and next state, there are some like mapping or transformation relationship. In general, your testing would require us to compute the Jacobian of the end state with respect to previous state and then calculate determinant. So this is not very easy in general. But but for Hamiltonian system itself, it's nice because this determinant is always one. So you really don't need to worry about that. That's why when we do the Mitropoli-Hastings testing, you only need to calculate the ratio between the joint probability of your sample proposal and the joint probability of your starting state. Right? So that's the benefit. That's why Hamiltonian system is so popular. But again, I want to emphasize, if you like to use other dynamic systems like large event dynamics to do that, you can do that. But you have to deal with this Jacobian issue. So and then we talk about in practice how we do this, because ideally, if you just evolve Hamiltonian system, because the energy is conserved, it doesn't change, your acceptance rate is always 1. However, in practice, you'll never be able to solve it accurately, right? You always have to involve some numerical methods, right? And once you use numerical integration to solve the system state, there's always some error. That means that you cannot escape the Mitropoli-Hastings testing, right? So the most commonly used method is called leapfrog method, right? So we have a talk about that. It's kind of a more advanced approach than the simple Euler method, the second order approach. And it also has nice properties because it also has the shear transformation. So if you run your leapfrog to solve the state of Hamiltonian system, then the determinant of the transformation, state transformation, the determinant of the Jacobian of the state transformation is still 1. So that's very nice property. That means if you use leapfrog, you don't need to worry about that as well. But because you are using leapfrog, you're using numerical integration, the energy won't preserve. So that means this joint probability, the joint probability of end state and joint probability of the initial state, they can be different. So that means your acceptance probability is not guaranteed to be 1, but still, like if you tune the leapfrog step size, number of steps, it can be very high. Okay. So this is the steps of running Hamiltonian sampling based on leapfrog method. So as we mentioned, right? So first, we're gonna generate a new sample for the momentum just from the Gaussian distribution. And this can be viewed as a Gibbs sampling step because this momentum R is totally independent to the random variable Z, right? So the prior is equal to conditional posterior. So it's equivalent to do a Gibbs sampling step. And then we initialize our current sample Z. Or initialize the state of Hamiltonian system with the current sample Z, and the R, the momentum sample we just generated, Then we run leapfrog for L steps with steps epsilon. Then we obtain the state Z prime, R prime. And of course, to ensure reversibility, we have to negate the momentum. Then we conduct the metropy testing. Like this is pretty straightforward. You just take a logarithm and take the XP, right? And then if this is accepted, then we use Z prime as our new sample. Otherwise, we keep Z. In this way, we finish one step of the HMC sampling, and we just repeat this step 1 and 2 until we get all the samples after Bernoulli stage. Okay, any questions so far? It's just a quick review of our last discussion. Right? Okay, so there's some kind of like interesting thing about HMC is that the generating of samples is kind of hybrid of random sampling and the deterministic transformation, right? So random sampling comes from the step 1, where every time you just randomly generate a new sample for the momentum, right? And deterministic comes from step 2. We kind of evolve the state of Hamiltonian system. This is totally deterministic. There's no randomness there, right? So people might be worried about whether this is correct. And first of all, we don't need to worry about detail balancing because step 1 and step 2 are both valid metropolis Hastings step. So step 1, you can show that keep sampling step is always a special metropolis Hastings step, right? The acceptance rate is 1. And step 2 is, although it's deterministic transformation, but you can view like conditional distribution is kind of delta distribution, right? Delta function. So by leveraging the theorem we used before, we can still show the detail balance with this acceptance test. So actually, the Hamiltonian Monte Carlo sampling, every iteration, it just combines 2 metropolis Hastings steps. So you can combine arbitrary number of metropolis Hastings steps, you still yield valid transition kernel. And then another thing is about ergodicity, right? Ergodicity means that you have to ensure your chain, right? Your chain is able to explore the whole space of the random variables values, possible random variables values, right? So, however, if your chain is not ergodic, it might be periodic. That means it might just restrict the small region. That's not good. So this could be some point to worry about, but typically ergodicity is still satisfied because we sample every time we just sample the momentum, and the momentum comes from a Gaussian distribution. This is typical choice. So the Gaussian distribution covers all possible regions of values that R can take. So you really can guarantee can further guarantee the ergodicity regarding Z. However, if your leapfrog happens to produce periodicity behavior over Z and R, then that is a problem. That means you might still like restrict the traversal of the samples into some trajectory, something like that, right? So in that case, we can overcome this issue by randomly choosing the step size and also the number of steps routinely. Like every 10 samples, we just randomly adjust the step size and the number of steps, and this can effectively avoid those behaviors and achieve ergodicity. So when can we apply Hamiltonian sampling? Or in other words, what's the limitation of Hamiltonian sampling? So first of all, we can see that it only applies to continuous distributions. Why? Yes, right. Because we assume our random variable can be Z, right? Can evolve along with time, and evolution is actually determined by the partial duality, right? So that means it is continuous, right? How do you calculate partial derivative of your energy with respect to a discrete variable, right? So, and also run leapfrog needs the gradient information, right? But other than that, in general, HMC is a very powerful Markov chain Monte Carlo sampling, and usually is much better than the ordinary metropolis testing. And for Bayesian neural networks, especially with the a fully connected architecture, HMC is usually viewed as the golden standard for the Bayesian inference or posterior inference. Actually, I got some project experience before for using this guy, and how many of you have heard of Bayesian optimization? So basically, is like, okay, I got some like black box function. Black box function means that I don't know the form of function. I can query the value of function at different inputs, but I will never be able to know the analytical form of function. Such kind of functions are quite ubiquitous in practice. Like if you want to tune the hyperparameter for neural network, right? So there is a mapping between the particular setting of hyperparameter and the performance, the accuracy on the validation data set, right? So can anyone write down a function that describes such kind of mapping? It's very hard. But we do have a need that we want to find the optimal hyperparameter that gives you best performance on some validation data set. So this is a scenario where you can apply Bayesian optimization or evolution algorithm, those kind of global optimization techniques. But for Bayesian optimization, you do need some probabilistic model to approximate a function. And every time, next step at which you want to query the function is determined by some so-called acquisition function. That acquisition function will integrate the posterior distribution or predicted distribution given the current data you have collected. So then the quality of this posterior distribution actually is quite critical or quite important for you to find the right function input to query at, because the less the number of queries you want, mean that you can the faster you converge to the global minimum. Okay. And we do find that in some of my previous projects, right, we use neural network to approximate a function, Bayesian neural network to approximate that function. We do find that if you use Hamiltonian sampling, it is better. And it's uncertain quantification and predictive distributions are all much more reasonable than other approximations like the variational approximations. And I think a few years ago when I joined some workshop in USC, some guy from DeepMind, they want to come out like they want to calibrate the quality of the posterior inference for a variety of methods, including the variational method, including the ensemble method, and also including the Monte Carlo sampling, this method. And they found that, of course, you don't really know the ground truth of the posterior distribution. So they have come out a bunch of other metrics. They found that the best quality is achieved by either Hamiltonian Monte Carlo sampling or random ensemble. It's very interesting, right? And variational inference is kind of like mediocre. But of course, there's no free lunch. Even HMC is kind of efficient, it's kind of nice, and usually it's still much slower than the variational inference. Okay. So now we want to talk about some kind of practical experience in using HMC or practical trade-off. So actually, the performance or the behavior of your Hamiltonian Monte Carlo sampling algorithm is sensitive, very sensitive to the choice of epsilon L. So epsilon here corresponds to the step size. Step size, you run your chain, you run your leapfrog to solve the system, right? And L is the number of steps. So you can imagine, given the same epsilon, the larger L, that means you're going to evolve your system to a longer time t, right? But at the same time, because every step they have some like numerical error, right? So the longer you evolve your Hamiltonian system with leapfrog, the more error will be accumulated, right? So you can imagine if you solve your system at time 0.1, it will be much more accurate than you get your solve your system at time equals to 100, because the error is kind of accumulated. So, but in whichever case, when you get the new state z prime r prime, you want to run this Metropolis Hastings test, right? So if you choose epsilon, the step size to be large, or the number of steps to be large, the benefit is that you essentially evolve your system to a very distant place, right? Because you evolve it for a much longer time. Right? This is d prime r prime, right? That will benefit you and will help you to explore whole space more efficiently, the space of the random variables values. At the same time, because larger epsilon and larger L will accumulate the errors faster, will more accumulate errors. That means your accuracy at larger t will drop quite a lot, so it will lower the acceptance rate, right? And on the other hand, if you set epsilon to be very small, we know that the smaller the step size, the more accurate your numerical solver, right? And also you choose L to be small, meaning that I don't want to evolve for a long time just to evolve here, right? So you can imagine your solution at this particular place will be much more accurate. That means your energy won't lose too much. So the acceptance rate will be quite high. So you can see the trade-off between the two, right? If you set a large step size or large number of the steps in the numerical integration, it can help you to explore the whole sample space more efficiently. At the same time, you accumulate more error, your acceptance probability drops. On the other hand, if you set your step size to be very small and choose a small number, just a few number of steps, well, you can imagine your numerical integration will be very accurate. The acceptance rate is very high, maybe 99, 0.99. But the price is that, okay, your new state, it will be very close to the current state. Right? You actually explore the whole sample space, not very efficient. So there's a trade-off. And in practice, it's very important to tune the two parameters. So basically, there's a kind of rule of thumb, right? Too high, I mean, the acceptance rate is too high is not good in running HMC. Perhaps in running Hamiltonian Metropolis, ordinary Metropolis is good sign, but for running HMC, it's not good. Because if you just set L to be small, epsilon to be small, it's very easy to get very high acceptance rate. And usually, my practitioners often suggest that you can tune epsilon L to maintain acceptance rate to be just 60 to 70%. That's the rule of thumb. In that case, like of course, you're gonna have a non-trivial chance to drop samples, but at the same time, you can quickly traverse through the whole sample space. Any questions so far? Yeah, that's a very good question. Actually, right now people people are not tuning epsilon L by themselves. Right now, the state of art is called a no U-turn sampling. And it's abbreviated as NUTS. This one is called NUTS. It's very well known sampling based upon this HMC. So it brings a smart strategy to automatically tune epsilon L or dynamic tune epsilon L. So don't need to worry about how do you set up the epsilon L. So I mean, if you guys are interested, there are a lot of like open source implementation of this NUTS sampling. It's kind of like standard in many probabilistic sampling strategy. Like even in PyTorch or TensorFlow, they have they have their own implementation of NUTS. But of course, if you really want to tune epsilon L by yourself, you can tune it. Any other questions? Yeah, great. So now we have finished the introduction of the Markov-Chain Monte Carlo sampling. So of course, this is a huge branch. We just discuss what are really fundamental, really important things. We want to deliver an idea. We cannot cover all the possible and also all the all the cutting edge progress on that. But I do believe, based on our introduction, it's very easy to get into the frontier research or state-of-art application of Markov-Chain Monte Carlo sampling, like NUTS. If you can read it, it's JMLR paper. It's just published a few years ago. It's very highly cited, and it's a very smart idea. You see that it generates tree paths into. It actually keeps a bunch of trajectories to select epsilon L. But anyway, after our discussion, we expect that you really understand the basic ideas or strategy of Markov-Chain Monte Carlo sampling. Is very different from it's a very different strategy from a variational inference. And also, what are key concepts to implement in Markov-Chain? What's the definition of the transition kernel? What's the meaning of stationary, invariant, equilibrium distribution? They're basically meaning the same thing. And what's the detail balance? Right? Detail balance is sufficient condition to show the invariance. Right? It's not necessary to, and perhaps it's the most convenient way to show the invariance. But it's not. But that does not mean like it is. If your transition kernel is invariant to the target posterior, that means the transition kernel must satisfy detail balance. It's not like a necessary condition. It's just a sufficient condition, a very wide use of sufficient condition. And also, the two types of strategies. One is called metropolis hasting, and what's the disadvantage? Random walk behavior. The advantage is very easy to implement, and disadvantage is called so-called random walk behavior. That means because you just blindly generate a new proposal, so there's a large chance that the proposal is rejected, doesn't pass the acceptance test. And then another idea is keep something. Keep something. It guarantees every time they're going to accept your proposal. However, because of the strong correlation of the new sample, of the new proposal and the current sample, so actually it restricts the efficiency to explore whole sample space. So actually, the limitation of these two types methods, metropolis hasting and keep sampling, represents two ends. One is that okay, I can freely explore the whole sample space if I just take arbitrary proposal generation distribution. Right? I can use a conditional Gaussian, but I can make the variance of Gaussian to be large. That means I can jump everywhere in the whole space. Right? Like if your current is the end, right? You make your proposal to be some conditional Gaussian. Right? You can make this variance to be very large, because that means your sample proposal is free to jump to everywhere. Right? But the problem is that it has much larger chance to be rejected. But if you use keep sampling, it specifies the proposal distribution is just the conditional posterior. Okay, the J given Z not I, and D. It guarantees the acceptance rate is 1. However, because the strong correlation between Zi and the Z not I, so actually every time you'll be close around this guy. So trade-off, right? And then hybrid Monte Carlo sampling can give you a much more flexible trade-off between the two. And the ideally hybrid Monte Carlo sampling in the Hamiltonian system, the acceptance rate is always 1. You can explore as long whatever long you want. However, because in practice you always have to choose some numerical methods to solve that system. That means if you run very long time and to get a distant place, to get a new proposal at a distant place, it's very likely you get it significantly drops the acceptance probability. So there's still a trade-off, but for hybrid Monte Carlo sampling or Hamiltonian Monte Carlo sampling, you have much more flexibility to choose between the two. And finally, you should be able to implement those algorithms. Okay, any questions so far? Okay. So now, from today, I think the remaining few lectures we're going to switch back to modeling. Right? So remember, if you recall how we're going to go through the discussion throughout the semester, right? At the beginning, we introduced some fundamental things about probability, basic concepts, the distributions, conjugate distributions, exponential distributions, their families. Those are kind of atoms or bricks to construct the probabilistic model. Then we introduced several general framework to construct or to design a probabilistic model, right? Like graphic models, like generalized linear models. Right? Those model too is very powerful, very expressive. You can use those kind of tools help you to design all kinds of like probabilistic models. But the problem is that, okay, even you have such a fancy model, you don't know how to compute, it's not meaningful at all, right? You want to, given the data, you infer something, you want to compute the prediction, you want to compute the posterior distribution, right? That will make your model useful. So then we switch to the computation method, right? This is another bottleneck or challenge for probabilistic learning, because you have an elegant model, and however, conditional data, the computation of the posterior distributions usually, in most cases, are not feasible. Except in several few cases, like only a few cases where your posterior distribution is easy to compute. You can use smart algorithm like message passing, like sum product algorithm to do that, right? However, in most cases, you cannot directly, you cannot calculate the posterior distribution precisely, right? So we have to seek for some approximation techniques. Then we introduce the two types of approximation techniques. One is called the variational inference, right? It takes the optimization view of the Bayesian rule, right? And then we kind of relax the optimization or constrain, essentially relax optimization, or either constrain the range of possible posterior we want to optimize, or we just relax the objective itself, right? That corresponds to the global and local variational inference, right? And also give a few examples to showcase how we apply variational inference. And then we switch to Markov chain Monte Carlo sampling, right? It takes another strategy to approximate the posterior inference. Instead, it never tries to work out a kind of like a analytical form. Instead, it just want to generate samples, right? If you can smartly construct a Markov chain, right, and it guarantees that in the limit, the chain will keep generating samples that exactly respect the target posterior, right? So now we want to come back to the modern perspective again, and to the most popular and the state of art probabilistic learning models. That is called Bayesian neural networks. I believe this will be very practical, because if you really want to use that, perhaps nowadays almost all people are using Bayesian neural networks, right? Rather than just use latent differential allocation or Bayesian logistic regression. So we're gonna first introduce the definition of neural networks and what's the backpropagation procedure and what's the idea of backpropagation. However, we won't talk about details of backpropagation because this is essentially an application of chain rules. And nowadays you won't need to implement backpropagation by yourself. It can be done very, very efficiently by mature libraries like PyTorch, like TensorFlow, or like I forgot. There are a bunch of like automatic differentiation libraries can do all those jobs for you. You don't need to worry about that. You just need to know the idea. And then we'll talk about a very popular technique to learn the parameters in the neural network is called stochastic optimization. Actually, the popularity or the dominance of neural network in the machine learning area, I think one important reason should be the success of the stochastic optimization. We'll talk about what is stochastic optimization, what is the idea. Right? Then we will generalize the neural networks to Bayesian neural networks. So we see what do you mean by Bayesian neural networks? Right? How do you introduce the probabilistic modeling in the probabilistic framework into the neural networks? Right? And then we will introduce one classical or popular posterior inference or Bayesian inference for the Bayesian neural networks, which is called Bayes by backpropagation. Okay. And we want to use this algorithm as an instance to showcase another very important trick or method in training Bayesian neural networks. It's called the reparameterization trick. So it's basically it's kind of like standard trick you're going to use in learning Bayesian or probabilistic neural networks. And then we're going to introduce two popular Bayesian neural networks. One is called auto-encoding variational Bayes. And the second one is called general adversarial networks. I believe you guys have heard of that before, right? GANs, general adversarial neural networks. Okay, so first we'd like to introduce what is neural networks, what is backpropagation. So neural networks, although it's very hot right now, but it's actually a very old topic, and I think the development or the development of neural networks have gone through like depression and resurgence. Depression and resurgence is kind of like a wave. It's not like a constantly growing thing. Right? So it can be traced back to 1943. These two pioneers have showed how linear threshold units can be used to compute logic functions. It's very, very simple. And linear threshold units, well, can be viewed as kind of like a ancestor or father of the ReLU activation function. And then in 1949, this guy and this pioneer, he's in psychology, he suggested a learning rule that has some logical plausibility. And then in 1950s, Rosenblatt have invented a perceptron algorithm. A perceptron algorithm is just a linear classifier. All linear classifier can be viewed as a particular type of neural networks. Then in 1969, Minsky and Papert studied the neurons from a geometric perspective, and they published a very famous book that make the interest of the neural networks into winter. It's like winter season for artificial intelligence because they show that the perception algorithm cannot classify XOR cases. Right? If you have taken my machine learning class before, you should be able to recall that. Right? There's a fundamental limitation of perception algorithm, so that makes the researchers' confidence about neural networks' future to reduce to the minimum, right? But then in 1980s, it kind of researched again with the development of convolutional neural networks and also redevelopment of the or invention of this backpropagation algorithm. And then in the 1990s, because of the invention of support vector machines, the neural networks has go down again, and all people like switch to support vector machines. But now, from 2003 to today, people found that if you have a large data, if your computational power is enough, like especially with the development of GPUs, people found that on the big data, neural networks really, really powerful in many scenarios, like image classification, like voice recognition, and even in some like areas like Go game. Like people never thought that the computer program can beat the world champion of Go game. But right now, neural network can do that. So we have to emphasize that neural networks are enlightened by the biological neural system. So basically, people have found that, like even in 19th century, right? People have found that for the brain or nervous system, the basic unit is the so-called neurons. Right? So there are two types of neurons. One is dendrites, one is axon or dendrites. Dendrites are here. Right? They are in charge of collecting information from other neurons. And axons just generate outgoing spikes. So if you just look at the data, like neural spike data, it just signals like this, a bunch of like spikes, and then we have like a varying gaps between those spiking signals. Like people are inspired by the biological neural system to invent the so-called artificial neural network. But want to emphasize, this is just inspiration. There is not any like fundamental connection between artificial neural networks and real neural networks. Like any serious neuroscientist won't admit artificial neural networks is a simulation of the true neural network, because the artificial neural networks, I mean, they don't have many fundamental properties of the real neural network system. It's interesting that I've talked to, several years ago, I talked to some guy in Google research. They're trying to construct artificial neural networks, kind of really mimic the biological neural networks. They want their neural networks to have some basic properties of biological neural networks, and then they want to train that neural networks and see what's the performance. However, that performance is much worse than artificial neural networks. Sometimes people, because of the engineering demand, right? Engineering need they define logistic function, define all kinds of activation function, they define their connection, the ways to connection, and they're not justified by any biological meanings. However, they're working in practice. If you really want your neural network to be like or similar to the biological neurons, it does work. That's interesting things. So if you in the future, if you read a paper and say, okay, we're building this network because human brain will work like that, and human and neural system work like that, don't take it seriously. This is just a kind of like advertising or the way to sell their idea. They're not scientific. Like you might have heard the idea called attention network, right? And those guys who highlight their attention ideas say, okay, because animals or people, or when they look at the pictures, they have some attention. They don't look at every pixel of the picture, just look at a bunch of trunks in that picture, right? So that makes sense, but they don't give any fundamental or prove any fundamental connection between the attention mechanism, visual attention mechanism, and the so-called attention mechanism implemented by the network. Attention mechanism essentially is just the kernel method. So again, I just want to emphasize this fundamental difference. Right? So neural networks shouldn't become neural networks. It's just the artificial model created by human beings. So what is this artificial neural network? So in kind of formal statement, we should say this is essentially a function that converts the inputs to the outputs defined by some directed acyclic graph. Right? So in this directed acyclic graph, the nodes are organized in layers. And those, I mean, oftentimes you see they call nodes as neurons, or neurons nodes are kind of exchangeable in the artificial neural network literature, right? And then on the edges, which connect different nodes, they essentially carry output of one neuron to the other. And this edge, those edges are associated with weights. So if we can take a look at this structure of the neural network, it's just one example. So we have 3 layers in the bottom. We got input layer. Right? So each node or each neuron in the input layer corresponds to an input feature. This might be x1, x2 to xn. Right? And then the input neuron will be fed into the next layer here, right? And how to feed them? It will be determined by the connection between each neuron in the input layer and the neuron in the hidden layer, and also the weights associated on those edges. And we're going to talk about how they're computed, in the next step. Right? And then when you compute the neurons in the hidden layer, and then you just throw the edges and weights to compute the neurons in the output layer. So that's the general idea of a neural network. So to define neural network, you need to specify the structure of the graph, meaning that, okay, how many layers we're gonna use, right? And how many nodes per layer, and how are those nodes are connected, right? The easiest one will be fully connected. That means each neuron in this layer will be connecting to all the neurons in the next layer. Right? But there are other ways to connect the neurons across layers, right? And also you need to determine the activation function on each node, meaning that, okay, when I do some linear transformation through the edge weights, and then I perform some nonlinear activation functions, and then use that as the input to the next layer. Like we're going to talk about them in a minute. Right? And then you have designed a neural network. The learning itself is essentially to infer edge weights from data. So the parameters of neural network are all the weights stayed on those edges. And the goal of the training essentially is to find the output weights on those edges. Okay? So what is activation function? So basically, activation function is just a scalar to scalar function. You apply some like transfer, and in most cases just nonlinear transfer. Suppose this is your output of the previous layer, right? And then typically for neural network, they're gonna first do some linear transformation of the output from the previous layer, and then they perform some element-wise activation function over that to get your output of this current layer. So what are commonly used activation functions? This is the most naive one. It's called linear unit. That basically means you don't do anything, right? And you do the threshold unit. That means for example, take sum of that, or you do sigmoid, 10H, or rectify linear unit. So these 3 are the most popular, right? And especially the loop, right? Rectified linear unit, as nowadays becomes a kind of like a standard choice of the activation function. Right? But in addition to this, there are more activation functions exist, like sine, cosine, Gaussian polynomial, etc. So basically, the choice of activation function is kind of arbitrary. You can choose whatever you want, right? But the most often choose will be this guy and this guy. So now, want to give a concrete example, right? How we specify a neural network and how, given the neural network parameter, we can make a prediction. Right? So this is basically a 3-layer neural network, and the input layer consists of x0, x1, x2. Right? So this shaded variables is just a constant 1 and 1. It's just like a linear regression model. I put some bias on parameter. Right? And then, as we mentioned, right, we attach a weight to the edge connecting every pair of the neuron. Like between x0 and z1, we attach a weight, right? And between x0 and x2, we got another weight. Here we just didn't write it down, right? x2. And for example, for the edge connecting x2 and z2, we got a weight w2 to h. And associated with each edge will be a separate weight. Right? And then, given this neural network, how do we calculate the final output, namely the prediction? Right? So we just do it layer by layer from top to bottom. This is called a forward pass. Right? How can we do that? We're starting from the input layer. Then we just compute the neuron or the output of each neuron in the next layer. And the computation is to first perform a linear combination of the values of the nodes connected by the neuron, and then perform a nonlinear activation. For example, here, to get the prediction, we're going to first compute Z1. Right? So Z1 is computed by a linear combination of all the neurons connecting to Z1 in the previous layer, which is the input layer, right? So it's a linear combination of x0, x1, and x2. As we mentioned, x0 is simply 1. And the weight is actually staying on the edge connecting to Z1, right? So for x0, the weight is W01H. So it's here, right? Times 1, because x0 is simply 1. Right? And then for x1, we're gonna multiply x1 with the weight on this edge, which is W11H. And then we weight x2 by W2 to H, which is on edge connecting x2 from x2 to z2. So you do the linear combination of the neurons in the previous layer connecting to the current neuron, right? And then you perform a nonlinear activation function. For example, it could be sigma, it could be tanh, it could be a loop, right? Then you calculate the value or output of the neuron Z1 in the second layer, right? And similarly, you can compute Z2, right? Again, a linear combination of the neurons in the previous layer, which is the input layer, and weighted by another set of edges, right? Because you have a set of new edges connecting from each neuron in the input layer to Z2, right? So accordingly, the weights on those edges are different. So you got W02H, right? So this is a W02H plus W12H. This is the weight down here, right? And the W22H here, right? And then after you do a linear combination, then you do a nonlinear transformation. that is nonlinear activation function, you get Z2, right? I will usually refer to this Z2 as the output of the neuron. And now we have finished computation of the output of neurons in the second layer, right? Remember, Z0 is simply 1. We don't need to compute it. And then we can use those values to compute the output of the neurons in the next layer, which is in the output layer. Right? So the output layer, we only have one neuron, which is Y. So the computation Y is simply a linear combination of the neurons, which is in the hidden layer, connecting to Y, right? It's W0O plus W110 Z1 plus W210 times Z2. Right? And one tradition in neural network modeling is that we do not apply nonlinear activation function in the output. We just do a linear combination. Someone may ask why. There's no reason. You just put it. If you feel upset, of course you can perform some nonlinear activation function accordingly. But I mean, by default, people just assume, okay, the last layer, your output is just linear combination of the outputs from the second last layer. Does it make sense? I think it's relatively straightforward. I believe most of you actually know that. So just to give a quick introduction. So in this way, you can see that the computation is starting from the input layer and then calculate the output of neurons in each hidden layer until you reach the output layer, right? So this is called a forward pass. And then your output of the neuron in the output layer will be the prediction, right? And of course, you can view output. The output of the output essentially is a function of x0, x1, x2, because you're doing a bunch of linear transformation and nonlinear activation function to reach output. So it's definitely a function. So that means you can construct the square laws for this example. For example, this is your prediction, this is your ground truth. So you can construct the square laws on that, and then you can minimize this loss because Y itself essentially is determined by all the weights on this neural network, right? So mathematically speaking, you can compute the gradient of loss with respect to the network weights. And if you can compute these gradients, then you can update these gradients, right? And suppose you have a bunch of data, you can just calculate loss gradient with respect to this neural network weights and update. Right? That's the way we train neural networks. So now, I'm gonna use a more succinct representation of neural network. This is different from the machine learning class. In the machine learning class, I only talk about this. Right? But right now, this advanced class, I'm gonna use a matrix and vector representation of the neural networks. So this is much more convenient and succinct in that we don't need to write down each element or each particular neuron, right? We just will the output of the neurons in one layer as a whole, just a vector, right? So we can denote all the neurons in the input layer by this vector x0. So you can assume the dimension is d0, so it's d0 by 1 vector. And then the neurons in the first layer, we can denote it by x1, right? And the second layer, x2, until the second last layer, xl minus 1, and then the last layer, the output layer is xl. We assume, okay, you got L layers, right? And then how do we represent the computation of the neurons in each layer, right? So consider a middle layer, J, right? If you want to compute the neurons, the output of neurons in that layer, which we denote by xj, essentially we first perform a linear transformation, right? You can write it as a matrix. So now all the attributes are organized into a matrix, right? And then times the output of the previous layer, which is xg minus 1. So you can imagine wg will be size of dj times dj minus 1. Okay? And xg minus 1, as we just defined, is dimension is dg minus 1 times 1. Right? So you multiply wg and xg minus 1, it will give you the vector of dj times 1. Right? And then we perform a analyzed nonlinear activation function. We get the output of the neurons in the layer G. Does it make sense? Right? It's just a standard. It's just you want to represent all those computations with matrices and vectors. You don't want to write down the linear transformation of each particular neuron. Right? You just write down the how we get them in each layer together. Right? And then we get the xg, right? The output of the neurons in layer G, and we can continue to do this and until we reach the layer xl minus 1, right? Once we compute the xl minus 1, the second last layer, we use them, we feed them to the output layer to compute xl, right? As we just mentioned, according to the neural network tradition, the output layer, the neurons all the output neurons are just linear combination of the outputs in the second last layer, right? So that means XL is WL times XL minus 1. Right? You don't need to put the nonlinear activation function in front of it anymore. And DJ or DK in general means the dimension of each layer or the number of neurons in each layer, right? And D0 actually is the dimension of input, right? And DL is dimension of output. Right? This is the general case, although in most cases, DL is simply 1. You know, just predict the scalar value. But there are some cases where you just predict the vector. Okay, any questions so far regarding the notations? Is everyone comfortable with this? Right. Yeah, because this is useful. This is useful notation because when you try to model a neural network, right, you really don't want to draw a figure like this, right? And just indicate, just denote what is the particular weight value on this edge. That's not necessary. It's really tedious, right? So we usually use this kind of notations to represent this series of linear and nonlinear transformation procedure. So, and when we write down the output of neural network, right, and we index all the edge weights, right, W1 to WL. Remember, WJ is actually connecting. This is W0, W1. This is WL. Oh, sorry, this is W1, W2 is WL. It's just the edge width connecting layer L minus 1 to L. Right? So we can index all those edge widths by this calibrated caliber W. And the computation of output is essentially a recursive application. Right? You start from X0 through some linear transformation, while W1, right? And then you apply sigma activation function. Right? Then you do a linear transformation again in the second layer, that is W2, and do a sigma activation function. You continue to do this until you arrive at the last layer. And at last layer, you only need to do one linear transformation, you get your output. So essentially, neural network is a definition of function, and the function has this recursive structure. That's it. So to compute the output, like, through the definition,
you need to start from the bottom level, which is the input layer, and sequentially go through each layer. So you starting from the input layer x0, and then through linear transformation and nonlinear activation function, you get to the neurons at x1 and layer 1 denoted by x1, right? And then do linear transformation, nonlinear activation equal x2 until you reach the output or the prediction XL. So this is called a forward pass. So in general, if we want to train a neural network, that means we want to estimate the edge weights, right? Those set of matrices across the L layers. So we just mentioned it's W1, W2 to WL, right? And suppose we have given like n training examples in our data set, we can construct the square loss, right? Because each prediction, right, for each example xn, is essentially a function of xn and parameterized by those edge weights in the neural network. So in principle, we can minimize this loss with respect to W, right? So and you can obtain optimal W. This is a training procedure. However, the computation of the gradient of the loss with respect to the neural network weights is non-trivial. It's not very easy because of this recursive structure. So the efficient method to compute the gradient with respect to those neural network weights was a hot research topic maybe 20 years ago. But right now, people have a kind of like agree that the backpropagation should be the most efficient algorithm. It should be the best algorithm to deal with that. So it's like the idea of backpropagation is like you reverse the computation procedure. Right? So we know that through forward pass, you start from the input layer and compute the neurons layer by layer until you reach the output layer, right? And when you compute the gradient, you're going to do this procedure in the backward. So you first compute the gradient with respect to the output and with respect to the edge matrix in the last layer. And then you go back to the gradient with respect to the neurons in the second last layer, and then the neurons, the edge matrix in the second last layer. You continue to do so until you reach the input layer. That's the idea. So the application of this and the backpropagation itself essentially is an application of the chain rule. So it's kind of a very smart leverage of the chain rule to avoid unnecessary duplication in calculating a gradient. Right? So suppose this is a loss, right? So the way to conduct backpropagation is that, okay, this is my neural network. Right? I'm going to first compute the partial derivative loss with respect to the output. It is the output neuron, right? And then we compute the partial derivative of the output neuron with respect to the edge weight in the last layer, which is WL, right? So the benefit is that if you want to compute the partial derivative of loss with respect to the weight matrix, I can just apply the chain rule. That means I just multiply partial L or partial neuron and times partial neuron with respect to weight. Right? And this intermediate results can be shared. Right? When you compute the partial derivative with respect to the weight in the lower levels, you first calculate the partial derivative with respect to the neurons in that level. And this is done by chain rule as well, because once you get this guy, and then you calculate the partial derivative of XL over XL minus 1, right? The neurons with respect to the previous layer. And then you compute the partial XL minus 1 with respect to the partial WL minus 1, meaning the weight matrix on that edge. And then just multiply together, you get this. Right? And similarly, you keep doing this, you move to the one layer below. You continue to do this until you reach the bottom layer. And then throughout this procedure, you can efficiently compute the partial derivative of loss with respect to every with matrix. Does it make sense? This is just a brief description of how we conduct backpropagation. But we're not going to cover details because of the time, right? We will not discuss details because it is quite mechanical and it's quite trivial. And nowadays, more important nowadays, you will never need to implement backpropagation by yourself. And it's basically, you can compute a bunch of like composite functions, right? And then we'll get the loss, and they can track all those partial derivative throughout the computation, throughout the forward procedure. So they can conduct backpropagation by themselves so that they can compute the partial derivative with respect to the target parameters automatically. So we just want to give you a sense about how these are conducted. Okay. So any questions so far? Everyone feeling comfortable with that? Okay. So next we're going to talk about the stochastic optimization, right? Yeah, perhaps we can stop here today because we only have like 2 minutes left. I think it's enough for us to finish the introduction of stochastic optimization. Okay, see you on Thursday.